It's called the CHSH game. I wouldn't recommend playing it at parties.
Greetings. This is The Filter with Matt Asher. Scott Aaronson teaches computer science at the University of Texas at Austin and is director of its Quantum Information Center. He's the author of Quantum Computing Since Democritus and runs the highly influential blog Shtetl Optimized. Scott, welcome to The Filter.
Thanks for having me.
It's great to have you here. Our main topic of conversation for today is randomness, a topic you've written about in papers and in your book. And it's one that's central to the work that you do. I want to start by noting, based on my own much more limited but still significant amount of time exploring the subject, that it's a hard topic to discuss because the words we use for it are often overloaded and assertions are highly contextual. So let's just start by a seemingly innocent question. Could you pick a random number for me right now?
I mean, I can pick one, but I can't guarantee you that it will be well distributed by any distribution that I've specified in advance. I could say 4, for example.
Okay, great. Thanks. Is that a random number?
It all depends on, you would need some prior beliefs about from what distribution was I drawing it, what is the process that generated it. This is part of what makes randomness hard to think about, right? We can never sort of put our hands on one specific sequence of numbers and say, this is random, right? What we can say is this was generated randomly. Even something with, enormous patterns in it would have some chance of having been generated randomly.
Right. I think that's part of the key is that when we can talk about a process that generates random numbers, but once the number has been generated, it's not really random anymore, is it? It's a known or a constant. And, there are lots of ways to generate those, and some are better than others. In my view, though, despite it being kind of a tricky subject, or perhaps because it is, it's one of the least talked about builders of modern society. All of cryptography depends on it, and that means all of modern finance and lots of other things depend on it. It's fairly important, isn't it?
Well, yeah, I mean, it is a central aspect of computer science, of cryptography, also of physics, of quantum mechanics, obviously, of economics, and the foundations of math and philosophy. But, there's no department of randomness studies that I know of. The study of it is very much split up among all of these different disciplines that study different aspects of it.
One of the things that I found when studying probability in university is that the notation and, in fact, the very framework that we have for trying to understand randomness mathematically essentially drains it of all meaning that relates to uncertainty. Is that your experience as well, or do you still see some residual uncertainty?
I think that if you're talking about the formalization of probability by Kolmogorov and others, in terms of sigma algebras and Borel measures, and there are good reasons why all of it was developed that way, right? If you want to talk about random events, in continuous spaces, right, you eventually need these notions. But these are definitely not the first things that I would talk about to someone who was just getting started in learning about what is probability. I would start with just, simple examples. I flip a coin, right? I walk randomly on a 2-dimensional grid. Will I eventually return to the place where I started? I tend to like to start with concrete problems and then only, develop an abstract theory later after a need for it has been established by needing to solve the problems.
Well, and that was how the theory initially was worked out by Pascal and others as they were trying to figure out a fair way to split a pot, actually, of a betting game that had terminated before it was supposed to be over. And they want to figure out if someone's ahead in this game of pure luck, how much of the pot is mine and how much is yours. And then that was, in a sense, I think was the foundations of it. So it was very much driven by a practical problem that people wanted to solve. Mm-hmm. As I was trying to get a handle on the part of randomness randomness that isn't just the pure mathematical part, I created a taxonomy of randomness. This was about 8 years ago, and it started with fixed numbers, constants basically, which are not random at all, up to martingale random and true randomness, if this indeed exists. And all of the lower levels of randomness are essentially epistemic in that what makes an outcome random is that we're unable to predict it with certainty beforehand. But there's a stronger meaning, which is that randomness is baked into our universe, and that no matter how well we understand the underlying process of events related to the quantum world, we'll never find a deterministic mechanism. So one piece of evidence for this, which you talk about, is that we are able to break something called the Bell inequality. And in doing that, somehow this tells us that there can't be hidden information there. Could you maybe explain how that works?
Sure. You're asking me about really one of the biggest developments in the history of science, right? But, I can try to do it in 5 minutes.
Take all the time you need.
When quantum mechanics came along a century ago, it was a theory that had probability sort of baked into it at a very fundamental level. If I have some physical system, could be an atom, could be a photon, in general, the best predictions that I can possibly make for it are going to be probabilistic ones. This is not because I lack sufficient knowledge, about the state of the photon or the state of the atom. This is because at a fundamental level, the state is, a type of object that is unfamiliar to our everyday experience called a superposition. To every possible place, for example, where a photon could be, quantum mechanics says I have to assign a number called an amplitude. Okay, amplitudes are related to probabilities, but they're not probabilities. In fact, they can be negative numbers, or they can even be complex numbers. Okay, and the rules of quantum mechanics do two things, right? The first thing is that they tell you how these amplitudes change over time. If I have a physical system that is, say, isolated from its environment, so Schrodinger's equation, which is the central equation of quantum mechanics, tells me that these amplitudes change over time by some linear differential equation. And then the second thing is that there's a rule for what happens if I look. Okay, if I make a measurement, then nature has to make a choice at that moment, right, of one particular outcome to show me. And the rule is that the probability that nature chooses a specific outcome is equal to the square of the absolute value of the amplitude of that outcome. So in this way, even though the amplitudes were complex numbers, I get probabilities. I get numbers that are real and that are from 0 to 1.
Right. So the amplitude maps to a probability that something will happen. It doesn't map to a certainty of what's going to happen. And we believe we can't go any deeper than that.
That's right. That's right. And if you accept that this is the sort of fundamental description of nature, then one doesn't expect to do any better than just giving probabilities. Because when I make a measurement of a quantum state, you can give arguments for why, the amplitudes sort of almost have to get mapped to probabilities in this way, right? Why a different way of doing the mapping, wouldn't even make a whole lot of internal sense. But there were people who were never happy about that, okay? Most famously Einstein, who in this paper with Podolsky and Rosen in the 1930s said, this can't be the final answer, right?
This is the God doesn't play dice with the universe.
So
idea,
yeah,
right?
I think he said that in letters or in a letter to a friend. Okay, in this paper in 1935, Einstein, Podolsky, and Rosen said, look, we accept that quantum mechanics makes very good predictions, but we think that there has to be some deeper thing underlying it. And the argument that they gave involved multiple particles that could be in entangled states. Right? Now, what does entanglement mean? Let's just, for simplicity, say we have 2 bits of information, right? I could just separately give each bit an amplitude to be 0 and an amplitude to be 1, right? By the way, a bit that can be in a superposition of 0 and 1 we call it a quantum bit or a qubit, right? These are the basic building blocks that we think about in quantum computing and quantum information, okay? But if I have 2 of these qubits, then I could also put them in a state where, let's say, there is some amplitude for them both to be 0, and there's an equal amplitude for them both to be 1, right? and there's no amplitude for them to be different. Okay, now this is called an entangled state, right? Like 0, 0 plus 1, 1. What it means is that the two qubits are correlated with each other. If I were to measure one of the qubits, and if I saw that it was in the state 1, let's say, then immediately I would know that the other qubit was also in the state 1, no matter how far away it was, right? Likewise, if I saw that it was 0. It's not just that, because qubits can be measured in many different ways, right? There are what we call different bases in which you could measure a qubit. I could, for example, instead of checking whether my qubit is 0 or 1, I could check whether it is 0 plus 1 or whether it's 0 minus 1.
So for the listeners, this is a little bit like, maybe to simplify, if you're looking at it from a particular angle, then it shows up as a 0 or a 1.
That's right. I can tilt my head. I can change the angle at which I'm looking at it. So I can choose how to measure my qubit. I can choose which two mutually exclusive possibilities I would like it to collapse to. And it will always collapse to one of those two randomly. And whichever one it collapsed to, the other qubit will collapse to the same one.
When looked at from the same angle.
Yeah, exactly. If someone else who looked at the other qubit from the same angle would see that it had collapsed in the same way. So Einstein, Podolsky, and Rosen called attention to that. And they said, well, this feels too much like faster than light communication. This sounds like our choice of how to measure the first qubit is instantaneously affecting the second qubit. And that ought to be impossible by, special relativity, that says that nothing can be transmitted faster than light. Now, when you think about it enough, you find that this effect, as striking as it is, cannot actually be used to send a message of your choice faster than light. And the reason for that is interesting. It's that, let's say that Alice has one qubit and Bob has the other qubit, right? Alice can always choose how to measure her qubit, but she cannot choose the outcome of the measurement. According to the rules of quantum mechanics, the outcome is random.
And she can't reach in there and twist the qubit and then have it twist on the other end.
Exactly. So she can choose how to make the measurement, but once she's chosen that, then the outcome is random. And so then what Bob sees, if he looks at his qubit, is a distribution over the two possibilities. But you can prove a theorem that says that that's exactly the same as what he would have seen if Alice hadn't measured. So the fact that Alice made this measurement is not detectable by Bob. So something weird is going on, that sort of our best description of nature seems to involve this faster than light effect, and yet you can never actually use it to send a signal faster than light. What Einstein and his collaborators said is that, even the appearance of this faster than light effect is sort of unacceptable, and we need a better theory that will explain where this is coming from. And the kind of better theory that he wanted would be of the following form. It would say that when these two qubits were produced in the first place, right? So in order to entangle them, normally, they would start out very close to each other, right? In order to, actually do the operation that entangles them. So we could imagine that at the moment when these two qubits were created, they engaged in some kind of secret conversation involving maybe some yet unknown particles or forces. But we could imagine that beneath the surface, maybe these two qubits flipped a little coin and they said, okay, listen, this coin lands tails. That means if anybody asks us, let's both be 0. Okay? Mm-hmm. So they sort of agreed in advance. Now, they would have to agree in advance on many different things. They would have to say, well, okay, and what about if anyone measures us from this other angle? Then what should we do, right? But maybe they agreed in advance about the answers to all possible such questions. And if they did that, then the fact that Alice looks at her qubit and immediately she learns something about Bob's qubit, you could say, it's no more mysterious than, if I wrote the same message on 2 slips of paper and then I look at one of the slips and now immediately I know what's on the other slip, no matter how far away it is, right? This is just correlation of a random variable. There's nothing new or mysterious here. A big debate ensued. Niels Bohr objected to what Einstein had said, although, to this day, people still argue about what Bohr was trying to say. He wrote in this incredibly obscure way. People had all these philosophical arguments about it, but it took another 30 years. It took until the 1960s for people to realize that there was an actual empirical question here. That discovery was due to John Bell. What John Bell said was, could we actually invent a theory where the two entangled particles secretly agree in advance and that would be able to reproduce the statistics of all of the possible measurements that Alice could make and of all of the possible measurements that Bob could make on the two particles? Right? Because the problem is this: the two particles can sort of agree in advance in some secret way on a bunch of correlated random bits. Then later they become widely separated. And then Alice's particle sort of sees what Alice is doing, but it doesn't see what Bob is doing. And likewise, Bob's particle doesn't know, which measurement Alice is applying. Can they actually get all the statistics right? And now Bell proved a theorem that says, in general, they can't. The way that we like to teach this theorem today is actually in terms of a game. Imagine that Alice and Bob are, in separate rooms. They can't talk to each other, right? And now imagine that we're going to challenge Alice with some random input bit, and we're going to challenge Bob with a different random input bit. And now Alice and Bob both have to produce output bits. And the rule is, if the challenges to them were both 1, then they should produce different output bits. In any other case, if one of the challenges was a 0, if one or both was a 0, then they should produce the same output bit.
Right. So it can be a bit confusing, but the bottom line is that they have to somehow coordinate their answer, but they can't coordinate their answer. So the question is, can they do better than chance? And in this particular framing of it, chance would be they'd be right 3/4 of the time if they pick the optimal strategy.
Exactly right. So this is a famous game. It's called the CHSH game. I wouldn't recommend playing it at parties or anything. What's important about it is that Bell proved that no matter what Alice and Bob do, if they live in a classical universe and if they can't communicate with each other once the game starts, then the best they could possibly do is to win this game in 3/4 of the cases. They could do that by just always producing 0 as their outputs, no matter what, right? And if they do that, then they're going to win in 3 of the 4 cases. They're going to win unless both of their challenge bits were 1. And that statement is the Bell inequality. So the Bell inequality is a theorem that has nothing to do with quantum mechanics. Actually, it's a limit of any classical theory. Okay, but then what Bell also discovered is that if Alice and Bob were wise enough to arrange in advance to share entangled qubits, then Alice can measure her qubit in an angle that depends on her challenge. Bob can measure his qubit according to an angle that depends on his challenge. They can both give answers according to what the outcome of their measurement was. And the entanglement will correlate their answers in such a way that they will win this game about 85% of the time, okay, which of course is more than 3/4.
Right, and so this is then interpreted to
So what this means is that, now there's a proposal for an actual experiment, right? This is not just philosophy anymore. We could now actually challenge Alice and Bob in this way, give them the entangled particles, let them have that, see if they can win this game more than 3/4 of the time. If we repeat the game, let's say millions of times, and, we collect all the statistics and we see that they reliably are winning it, more than 3/4 of the time, then by Bell's theorem, this has no possible explanation in terms of Alice and Bob secretly agreeing in advance on some shared classical bits. So this tells us, first of all, that quantum entanglement is a real phenomenon in the universe, that it is not explainable in terms of what today we would call local hidden variables. That is, the kind of thing that Einstein, Podolsky, and Rosen wanted. It is not explainable by the particles just secretly agreeing in advance on the outcomes of the measurements. This was sort of the original point of it, right? And when Bell proposed this in the 60s, this was really just, a thought experiment. But by the 80s or so, technology had improved to the point where you could actually do this experiment. And people like Lon Aspect started to do it using entangled photons that were measured at long distances from each other. And, the results were 100% consistent with quantum mechanics. For a few decades, there were some loopholes in the experiments that maybe, allowed the local realist diehards, a little bit of a way out. Maybe it was just a flaw in the experiment. Maybe Einstein was still right. But just a few years ago, the first experiment was done that I think, closes all of the reasonable experimental loopholes. And the result is that you still win this game more than 3/4 of the time. This is a really, really challenging thing to get across for popular audiences, right? And the reason is people tend to think either the world is normal and classical, or else there's all these spooky connections that let you communicate faster than light, right? And if you tell them that one of those things is not the case, then immediately they jump to the other extreme, right? And the truth that we've learned from quantum mechanics is that it is something intermediate between the two, right? I think something that is weird enough that before quantum mechanics, like no science fiction writer would have even had the imagination to invent this as a logical possibility. This violating the Bell inequality, it's something that if we wanted to do it, let's say in a world that was secretly classical, or, if we wanted to simulate our world on some classical computer running a simulation, like in the Matrix movie or something, right, then our simulation would need faster than light communication.
So the existence of the quantum allows us to do these things without violating the rule that you can't travel faster than the speed of light and that you can't send things.
Exactly. So quantum mechanics does not let us send a signal faster than light, but it lets us do these weird other things like coordinating in this game that in a classical world would have required faster than light communication.
Got it. Before we kind of move on, and actually do want to talk a little bit about that idea of the simulation, but before that, I think that the problem I have, at least as someone who doesn't know these things that deeply, with the attempts to prove that the universe has true randomness or that these can't be hidden deterministic effects that are just kind of behind the veil and we don't see, is that whatever you do in any of these thought experiments or real experiments, you need a seed for kickstarting the random number process, the generation process. I believe actually in your own words, it's provably unavoidable that you need this. So the proof here has to depend at some point on randomness, and we haven't proved that randomness is true randomness. Does that make sense as an objection?
Yeah. So those are good questions. Let me just back up a little bit. I mean, the original point of the Bell inequality was to sort of demonstrate that entanglement is real, demonstrate that there are no local hidden variables, that, Einstein was wrong about that. Starting around 15 years ago, some people noticed that once you've demonstrated that, then as a byproduct, you've also demonstrated something else, right? You have demonstrated that there must have been some true randomness in the outcomes that were generated by Alice and Bob.
Even though in the game, the inputs are decided by human beings randomly or by a computer or whatever, right?
Let's just grant for now that the challenges to Alice and Bob were random. Let's just grant that for the time being, okay? Then you could never know that there was any additional randomness in the world besides, that which you would already put into it. But this is not the case. One can argue that the outputs generated by Alice and Bob, cannot have been secretly predictable, even knowing the whole previous state of the universe, including all the challenges that you sent to Alice and Bob, including any hidden variables, or if they were predictable in advance, then you would have needed faster than light communication to coordinate them. That's the kind of conclusion that you're able to draw. And in some sense, this is really just a restatement of Bell's theorem. One argues this by saying that if Alice's and Bob's responses were secretly determined by information that was local to them, including the random challenges that they got, then that would have been a local hidden variable theory, right? Which is exactly the thing that Bell's theorem rules out. So then people started thinking, could we actually exploit this in practice? It hadn't even occurred to anyone that the Bell experiment might have a practical application. It sounded like either physics or maybe even metaphysics, right? But people started thinking, well, could we use this to get a cryptographically verified source of random bits? That we could use for various applications where you need certified random numbers. And, the idea would be to take the responses that are generated by Alice and Bob, check that they do indeed win this CHSH game more than 3/4 of the time, right? That they are indeed violating the Bell inequality. And then if they are, then, exploit the theorem that says that there has to be some genuine entropy in them. And so then we can sort of process that, we can refine it, we can use it to get some bits that we know are close to uniformly random, that we could then use for encryption, for example. Okay, so this was a very striking idea. People started developing around 2006. And as you just pointed out, there's an immediate problem with the idea. Okay, there's a fly in the ointment, and that is that in order to even get the Bell experiment started in the first place, we need random challenges to send to Alice and Bob. So it's like we need to invest randomness in order to get back randomness, with this kind of scheme. So you could say, even if it's interesting, it seems a little bit like present day nuclear fusion reactors. Yes, they generate power, but you need more power to run them than they're generating. So there's not yet any net gain. This is where it gets a little more technical. But what people discovered how to do was to be very, very judicious with the use of the randomness, for generating the challenges to Alice and Bob. So you could just only very occasionally put a tiny bit of randomness into the challenges, just enough to keep Alice and Bob on their toes, as it were, so that they know that in any given round, maybe you're really seriously checking them and maybe you're going to catch them if they're cheating. And as long as they know that, then you kind of force them to be honest in all of the rounds, even the ones where you're not using new randomness to generate the challenges.
Oh, that's interesting. That's almost like you're doing this as a game theoretic thing.
Well, yeah, the way that we would say it is that you're designing a protocol, to achieve something that you want. A key fact here is that Alice doesn't know which challenge Bob is getting, and Bob doesn't know which challenge Alice is getting, right? And so even if I kept giving them like a null challenge, like let's say I gave them both zeros, right? Even if that's the case, as far as Alice knows, I might have given Bob a 1. And as far as Bob knows, I might have given Alice a 1, right? And because of that risk, I can force Alice and Bob to sort of respond in the genuine quantum mechanical way, as if I was sort of challenging them randomly.
And the assertion there is that even if you do that, even if you give them what is obviously not a string of random inputs, but just a constant set of zeros or ones, that nonetheless, if they're playing the game properly, what comes out of it will be true randomness.
Yes. So the upshot of all of the theorems that people proved about this was that from a fixed initial investment of randomness, so let's say, you start out with maybe 100 or 1,000 random bits, let's say, you can then keep doubling your investment forever, right? You can get an unlimited amount of additional random bits by playing this CHSH game with Alice and Bob. So you need some initial random seed. You need some small seed, and if you have that, then you can sort of keep Alice and Bob on their toes forever. Keep them from predicting the next thing that you're going to challenge them with, and therefore force them to give you more genuine randomness.
Even if that initial seed that you use is not at all random itself, per se.
The initial seed has to be not known to Alice and Bob. If they in advance know everything, I said that people have done Bell experiments, in a way that closes all of the experimental loopholes. But there's one loophole can never be closed, even in principle. This is the one that's called super-determinism. I personally regard it as a little bit ridiculous, okay? But what it says is, well, suppose that the entire history of the universe were completely deterministic, And, in particular, how Alice and Bob were going to choose to measure their particles was also determined from the very beginning of time. And when the two entangled particles are created, then they somehow they already know how Alice and Bob are going to measure them in the future, right? Because that was determined from the beginning of time. And therefore they coordinate, using that knowledge. You could say philosophically, this can never be ruled out. There's a famous physicist, Gerard 't Hooft, who even advocates this. But my personal feeling is that, if that were to be accepted, then we might as well say, science has had a good run for 400 years since Galileo. It's time to throw in the towel. Because by that kind of conspiracy theory, you could explain absolutely anything. It would leave utterly mysterious, why are we only able to use entangled particles to violate this Bell inequality? Why can't we also use them to send information faster than light?
Right. It's kind of like a because God said it was going to be that way explanation.
Exactly. If this is allowed as an explanation, then because God said so is also allowed. Right. This is directly related to the point that we were making about these randomness protocols, right? That if you could say if everything is completely determined, so in particular Alice and Bob already know every challenge that could possibly come to them, then you can never even get started, right? You can never even bootstrap your unpredictability.
Okay, so if I'm understanding this, essentially what you're doing is that you are taking epistemic ignorance, the fact that from their perspective this is an unknown, and that you're converting it into true randomness. Would that be an accurate summary of what we've done?
Or we could say we're taking a small amount of randomness and we're converting it into an arbitrarily large additional amount of randomness.
Yeah, I don't like that as much because then I still think, okay, well, is that first randomness true randomness?
The initial randomness, it didn't have to be uniform necessarily, right? But I mean, anytime, something is unknown to someone, right, we could try to quantify that with some probabilities somehow, right? If people are hardcore Bayesians, then they'll say that all uncertainty, can be represented with probabilities, right? It's just that sometimes we wuss out. We don't actually go and write them down, right? But they wouldn't admit the existence of any kind of uncertainty that is not ultimately probabilistic. Now, I'm not sure that I would go that far. We need some initial unpredictability in the challenges that are sent to Alice and Bob. And then once we have that, then we can bootstrap and we can turn it into an arbitrary amount of additional randomness.
Got it. Mm-hmm. So just looping back a little bit to what you mentioned about the matrix, I did, for the listeners, an episode on the simulation hypothesis, or the idea that we exist in some kind of simulation, which might be a wetware simulation. It doesn't necessarily have to be in a computer that's just limited to zeros and ones. And I want to throw out to you kind of my own pet theory about this, which I'm not sure I believe, but that talks about or tries to explain why we might be in a simulated universe and what the purpose of that might be. So we know in our own universe that there are some problems that can't be solved in a closed form, in a deductive reasoning kind of way. Turing tells us this, Gödel tells us this. And if this is true in our own universe, as a matter of pure logic, it's quite reasonable that if there is a universe above us, that universe might have the same problem, and that there are problems for them that cannot be solved in a straightforward deductive reasoning way, that they have to be solved iteratively with, in a sense, Monte Carlo simulations, perhaps.
Well, I mean, even with Monte Carlo simulations, we still can't reliably solve the halting problem or things like that.
Right. This is true. This is true for us. But suppose, for example, that you are us, and that you have a particularly difficult problem. It's highly complex. There's lots of moving parts. It's not clear that there even is a solution to it. One of the ways that you might try to go about solving that is by creating a simulation. In fact, that's often what we do. Now, the frightening thing to me is, what if the problem that we are here to solve for the universe above is how to not self-destruct? So any civilization, any entity that's sufficiently complex and sufficiently powerful is going to have the ability to destroy itself. So if you were such a civilization and you had to solve that problem, well, what would you do? Maybe you would create a sub-universe dedicated to trying to solve that problem. and then you'd fork it if it went awry, or, evolve it using some sort of a genetic algorithm or whatever else it is that you need to do. What if we are created as a simulation in order to try to solve that problem? And of course, that means that most likely the end result of this is not good for us, because you wouldn't be trying to solve it if it didn't in the simulation end badly most of the time, or, with almost certainty, right?
Okay, so those are very big speculations, maybe a little bit far from the topic of randomness.
Here's where I need to fit it in. I don't think I did a good job of this. The idea basically is that human beings, that we are essentially dice, and that we are created to be dice in effectively a Monte Carlo simulation. And the fact that we have consciousness and some kind of self-reflection, or maybe baked into our universe, is this randomness, in quantum theory, means that it is capable of trying to solve problems in this space that's a very multidimensional, open-ended space for problem solving. Does that make sense then, and kind of tie it together?
I guess I would say a couple of things about it. The first is that I don't see evidence that our universe is designed for solving one specific computational problem. If it was, then it seems like so much of it is just a tremendous waste. Stars, burning themselves out, billions upon billions of them to no obvious purpose. Of course, the universe might have some purpose that eludes our understanding, or is utterly beyond, what we with our limited perspective can see by looking at it. If we believe that the world is quantum mechanical, in some sense, randomness is constantly being produced everywhere. Right? At least if we look at the actual macroscopic degrees of freedom where visible objects are in space. On every planet and every star, there doesn't even have to be life there, let alone intelligent life like humans. As long as quantum mechanics is operating, then anyone who was there would see all of these apparently random events, which, ultimately just come from the fact that we have this superposition with all of these amplitudes, and all that can get seen in sort of our ordinary three-dimensional space is a particular sample from this distribution that's defined by the squared absolute values of the amplitudes. So I'm not sure that, if someone did create the universe as like a gigantic Monte Carlo simulation, or, a gigantic experiment involving randomness, I'm not even sure that humans would necessarily play any special role in that experiment, right? We might just be some epiphenomena, like some scum that forms on the surface of a particular rock.
It's certainly a possibility. We're just speculating here, but let me just try one more approach to this, which is, what is our biggest challenge as a species? I would say it's, how do we avoid blowing ourselves up or destroying our world, right?
That is certainly a big challenge.
And if we were going to try to solve that problem, and we had really high level of computational sophistication, which we're beginning to get, how would we do it?
The question of how we as a species avoid blowing ourselves up is definitely a much, maybe bigger question than anything about randomness, or maybe from some people's point of view, a smaller question, because it's merely a provincial question about this species that happens to be on Earth, whereas some of these questions about randomness are sort of universal significance. I am certainly, extremely concerned about the question of how do we survive as a civilization. I would say that I am especially concerned right now. I think that we're in unbelievably perilous time for our civilization right now. Maybe one thing that could be relevant to say at this point is that people argue about how to think about quantum mechanics. And so, for example, if we kill ourselves off, is there also a branch of the quantum state of the universe that is equally real, in which we lived, in which we colonized the galaxy, or, flourished for millions of years or whatever? And conversely, if we live, is there another equally real branch of the quantum state of the universe, with some other non-zero amplitude in which we kill ourselves out. So people who believe in what's called the many worlds interpretation of quantum mechanics would believe that all of those branches are real. In fact, from their point of view, what we perceive as the randomness of measurement outcomes in quantum mechanics is really just an illusion, right? It's just our local parochial perspective because we only find ourselves in one of these branches.
And yet, so all of the outcomes did happen.
Yeah, they would say that
we just happened to be in one of them.
Exactly. Exactly. So from their point of view, sort of globally, quantum mechanics is actually a completely deterministic theory. It is only a probabilistic one as experienced by sort of beings who are inside of the quantum universe. Now, one thing that I wonder about, I'm not sure what the answer is, but let's say you believe that, and let's say that we do kill ourselves out as a civilization. Well, then, should we be happy that there are these other branches that survived and flourished? Or, should we be sad that we don't get to be in those branches and that we're stuck in this one?
Well, I certainly hope that we're on the branch that survives. And if I was given, $100 billion to try to solve the problem, I'd build a simulation and I'd build one as sophisticated as possible that mimicked us as closely as possible and see if the people I simulated could figure it out for me.
That's one way. I mean, you could say more broadly, there are lots of people, working on AI, on deep learning, right? We witnessed this spectacular success just, within the last year of this GPT-3 engine, this engine for text prediction that, is not a general AI, probably not even close to one, but it is doing things that would have surprised me a lot 5 or 10 years ago if you had told me that they could be done now. You could either hope or fear that, before we kill ourselves out as a civilization, that AI will just become smarter than us and then, either solve all of our problems for us or else, maybe just kill us all off, because
my money would be on the latter.
we're just getting in the way to it solving its own problems. If the ordinary things happening in civilization, other than AI or simulated realities, if those are depressing enough or scary enough, then some people might prefer to just roll the dice with the AI. Take their chances with it.
And let it try to figure things out. So kind of related to that and to the general idea of, scary uncertainties, let's just say. As a final thought, I was wondering, so the foundations of the subject that you work in have a lot of uncertainty, and this may not be unique to your field, but folks in engineering, they don't have to worry that F equals MA will be overturned for everyday application. But one of the most fundamental ideas of computer science, that P is not equal to NP, you've given a 2% chance, I think, of being false, as a rough estimate. And if it is false, then that would destroy essentially modern banking overnight or within a very, very short period of time. What is your relationship to that kind of level of uncertainty in your field? Do you think about it? Is it exciting? Is it scary? Does it mean that you're playing for real stakes? How do you think about that?
It's an interesting question, but thinking about it, I'm not actually sure that the situation is that different than in other kinds of engineering. Because, computer scientists are able to build systems that demonstrably work for a certain task, like, a file system, a sorting algorithm, right? And these work, in the same sense that a bridge works. They're built to certain specifications. Sometimes you can even prove that a specification is satisfied. But, even more relevantly, you could have millions of people relying on this thing over a long period of time. Maybe some problems come up, you fix them as they arise, and you empirically see that the thing works. Now, cryptography, which you mentioned, your question, is kind of a special case. Because in cryptography, it's inherently a paranoid endeavor, where you're thinking about what is the worst thing that an adversary could possibly do to me. And so the analog of that in engineering would be like designing a building that no criminal could ever break into, right? No matter how smart they were or something like that. Even if you're a structural engineer, it's very hard to make that kind of claim about a building, right? You can say, here's why I think this building will stand, why it's not going to collapse. In order to know that no thief could possibly break into your building, you really have to red team it. The only way you're ever going to know that, the only way you're ever going to get confidence in that is if people actually try to break into it and they fail. And even then, all you'll know is that, well, no one has figured out yet how to break into it, and maybe someone smarter could break into it in the future. Now, an encryption system is kind of like that. Its security sort of rests on a negative statement, right? It rests on a statement that no one, however clever they are, is going to be able to break the system and get my key in a reasonable amount of time. That is inherently a much harder type of claim to test than just, does this program produce the output that it's supposed to? Does it sort of work according to specification? There is some hope that, statements of that kind could someday be rigorously proven, right? Which, the very fact that there's even a hope of proving it is something kind of special about computer science. But yes, the hope of rigorous proof would depend on proving things like P is not equal to NP.
Right. I see what you're saying about that. If it turns out Bernoulli was wrong, then all the planes don't fall out of the sky at once. But if it turns out that our intuitions about solving particular kinds of mathematical problems, if it turns out that that is much easier than we thought it was, then the implications are very dire for a lot of industries very quickly, no?
Yeah, but if it turns out that there are invisibility cloaks, then all of these buildings that we thought were safe can now be broken into, right? It's very similar to that. We do have things in computer science that are analogous to the planes that stay in the air, the underpinnings of the internet that mostly work. Sometimes they don't work, but also sometimes planes crash.
Scott, thanks so much for coming on The Filter.
Of course. Thanks for having me.
Thanks for listening to The Filter with Matt Asher. You can find show notes at thefilter.org or follow user Matt Asher on the socials.